Konnichiwa. Hi, everyone. I love to see all of you here. I'm so honored and happy to be here and excited to tell you a little bit about our journey on machine learning at Woven by Toyota and maybe some of the challenges we've faced. So today, I'll cover why machine learning is important, especially in the field of autonomy. Then I'll talk about the evolution of autonomy itself and how we got here. I'd love to talk about what we are building and what you will need to build if you want to enter the world of data-driven autonomy. And of course, I'll talk about the challenges you will face from your accountants and your financial planners and your business plans. I'll also talk about what organization you will need. So we will focus on a holistic aspect of data-driven autonomy. And towards the end, I'd love to share what my team is doing here at Woven by Toyota in our automated driving business unit, and also show where we are headed. But before that, I'd love to introduce myself. So my name is Dushyant Wadivka. I am the global head of automated driving in Woven by Toyota, and I have been working on safety-critical software for 25 years now. I'm looking forward to retirement soon. But not until we make autonomy a success, and not until we help accelerate Toyota's vision of zero accidents, mobility for everybody, and an increasingly improving autonomy experience every day, every time you get in your car. That's my vision, and that's why we are here. My background is technically mechanical engineering, but I've only done software engineering for a long time. I have a background in control theory. My first half of the career was focused on control theory and vehicle dynamics. And then the last 10 years, I've focused myself on autonomous development. I worked for a long time in a company called Bosch, where I worked on level 3 systems or conditional autonomy systems with North American OEMs. And then for the last 10 years, I have been working in startups. I worked with Cruise in San Francisco on level 4 robotaxis in the cities of San Francisco. And then in Austin, I worked with Torque Robotics on level 4 trucking. I feel I've found my true purpose at Woven by Toyota because at the scale we are working on all levels of autonomy to improve, again, as I mentioned, Toyota's goal of zero accidents, mobility for all, and an improving autonomy experience. With that, let's jump into the topic. Of course, let's start with why machine learning. I'm sure you've heard enough of machine learning, AI. We need to take a step back and understand why this is important. Now, rule-based systems are already existing in the market. Some of you must be driving cars today that have that system in your car. And it's working quite well. And so that's not the issue. The issue is, where does it scale? As you know, driving is a very nuanced activity. And it has so many permutations and combinations. Driving in the daytime, nighttime, Japan, America, there are so many variations in the input. And if you have a system that doesn't have a fixed transfer function between the input and output, a rule-based approach will struggle. Because every time the inputs change, that definition that you have, that transfer function that you have, may not work. And you will have to reprogram it. You may have to tweak it. And yes, of course, you can do that. You can keep doing that. But eventually, you will hit a wall where you can't do that. No matter how much effort you put in, no matter how many if-then-elses you put in, you cannot cover all the scenarios that you will see. And at some point, that's where a tool like machine learning really lends its way to a good application. Why? Machine learning generalizes. It looks at a bunch of inputs and creates an output. And it doesn't even matter if it's never seen that input before, it will still generalize. And in the act of automated driving, especially if our goal is zero accidents, we must be able to handle not only what a known scenario is, but also handle what an unknown scenario is, stuff that we cannot program for. This is why most companies who are on this journey, like us, have decided that this is the way to move forward. We also believe this is the way to move forward. Let's talk a little bit about how we got here. So I've been in this space for a long time, as I mentioned before. I'm really looking forward to retirement already. But when we started, it was very clear. There were two camps. On one side, there was the evolutionary approach. They wanted to make incremental improvements, go from ACC to slightly better ACC. ACC is adaptive cruise control. They want to go from lane keeping to slightly better lane keeping. And this is an evolutionary approach. You keep improving your code. You keep tweaking your code. And it worked, because at that point, these systems were deployed on fairly cost-effective ECUs. And that's a very solid approach. There was another camp. The other camp said, nope, no evolution, revolution. We're going to go machine learning all in, because we are solving a different problem. Not this driver assistance problem. We're solving an automated driving problem. That's a different problem. And so we need machine learning, and we need big computers, and we need lots of sensors. And that was the other camp. And this really survived for a long time, until the industry began to realize one thing. There's actually a lot more similarity between those two parts than there is differences, especially when you think about the intelligence, especially if you think about the software that powers these systems. Because if you think about it, whether it's an advanced driver assistance system that just maintains distance from the car ahead of you, or a robotaxi that drives by itself in a complicated city environment, both these systems go through the same thinking process. The same thinking process that you guys go through. You see something, you understand something, you perceive something, then you make a decision. What do I do in this situation? And then you act on this decision. That is what we call by the stack. And that is one stack that can do these functions, regardless if it's deployed in a level 2 system or in a level 4 system. And that understanding happened in the industry recently, because the engineers they needed for this side were the same engineers they needed for this side. The other things have also changed in the last 5 years. I'm sure you've noticed. Machine learning has become very popular. Compute has become very efficient. You can stand up a system very quickly. Data has become very prevalent. So some of the challenges that you had 5, 10 years ago with cost and data seem to reduce. The compute is cheaper. You can run machine learning in the car. There's plenty of experience now. And that's why this convergence is happening in the industry, where at least from a software perspective, at least from a stack perspective, it doesn't make sense to build it twice. Now, if you want to build this machine learning stack that I just talked about, that can handle different cars, different sensor types, from a pickup truck, from a Tacoma to a Corolla, from 5 radars to maybe 7 radars, to LiDARs, to cameras. This stack has to scale across different vehicle configurations. To do that, you must be able to teach it, for the stack to learn. And for a stack needs, any kind of machine learning system needs infrastructure, needs a data-driven, a data flywheel, what we call the active learning loop. Hopefully, some of you might have seen that in Area 2, and hopefully my team did a good job of explaining that that is the backbone of any machine learning transformation. Before you decide you want to be machine learning forward, you have to build the infrastructure. And this infrastructure allows us to collect data from hundreds and millions of cars, look at that data, clean it, filter it, curate it, make it very specific to what we want to learn. For example, if we are having a tough time being smooth in a lane change, then we need to find data specific to that smooth lane change so that we can train our system to do a smooth lane change. That is non-trivial when you look at gigabytes of data. So you need systems that can look at that data, train from that data, develop the models, simulate and verify, test it, validate it, and then deploy back to the customers. That loop here has to be automated. Because if you do it manually, then you haven't really won anything. So of course, we have to automate that loop. That infrastructure is the backbone of a successful company or a successful transformation to machine learning. Now, the second piece is, how do you know you're improving? How do you know, despite all this cost and effort, that you're actually making progress? So then you need very quantitative metrics along these loop to see, yes, first of all, we're collecting the right data. True. Are we actually training efficiently? Is the model actually learning? Is it getting smarter the next time I train it? 3, is my performance actually improving, even though the model might be learning really efficiently? All of these aspects have to be looked at. And of course, they have to be automated and supervised by engineers and experts to make sure that this loop is not just running, but running correctly and efficiently. And lastly, you have to talk about volume and diversity. You can't just collect any data. Of course, you have to collect a lot of data, but diverse data. Diverse data means different kinds of data. This is a very simple chart you see at the bottom right here. How many times have you seen a horse on the road? Maybe a show of hands? Oh, at least a couple. Maybe it's not as rare as I thought it was, but it definitely doesn't happen all the time. Now, how many times have you seen cars on the road? OK, yes, good, good. So what I'm trying to show here is, of course, you have to look at both spectrums. There is the commonly found objects and rarely found objects. And that's what we call in the industry often the long tail. And for us to achieve our goal of 0 accidents, we have to cover the entire spectrum. To cover the entire spectrum, we have to drive a lot, but drive in a certain way and collect data in a certain way, or generate data in a certain way with synthetic simulation. These are the foundational investments you would need to be successful. Who is going to do that? You need people. You need talent. And that's where it's very different from conventional industries. I want to point your attention to 2 things. One is almost agnostic of machine learning. It's just a philosophy of how you build an org. If you build an organization that looks like your product, it'll work, versus a product that looks like your organization. What do I mean? So in machine learning or data-driven autonomy, there are few critical steps that we have to do. One, as I mentioned before, we have to build this off-board infrastructure, this active learning loop. That's one thing. Then we have to build the onboard machine learning stack. And then finally, it needs to work. So we need system integration of the stack. The software has to meet hardware. It has to actually run on a car. It has to meet non-functional requirements. It has to meet safety. It has to meet quality. It has to meet cost. It has to meet budget. This system integration is non-trivial. These are 3 critical activities that happen. And your teams should look like that, so that you have clear accountability, clear ownership, and clear distribution of work. And of course, team A and B and C have to work together, of course. But they have also unique responsibilities and unique accountability. This is critical in how you shape up the org. This will really help you accelerate your transformation to a data-driven organization. The second is, who should be in that organization? Who should be in these teams? And this picture looks very different from some of the current organization talent that we have. As you can see, this is just a representation. These numbers are just proportional, just to highlight my points. The order flips. The domain experts, very important, but not in terms of volume of domain experts. You need a few key experts who understands how controls work, who understand how perception works, who understand how localization works, who understands how vehicles work, who understand what feel is. But what you really need is core machine learning engineers and software engineers who can build that infrastructure for you. That is agnostic of the application. And so what you really need is true software engineers, and a whole bunch of them. What you also need is simulation. We haven't talked about this enough. But imagine, I can't keep driving forever to find a horse. Some of you are lucky. You found a horse. But if I'm looking for a rare event, I may have to drive millions of miles. Can't do it. So we need simulation. We need lots of simulation, and that becomes the backbone, not on-road testing. And lastly, data scientists. This is very important. This whole discussion is about data. How much data do I need? I need a data scientist to answer that question. Do I have enough data? I need a data scientist to answer that question. Do I have the right kind of data? I need a data scientist to answer that question. Are my models learning? I need a data scientist to answer that question. Am I improving my performance? I need a data scientist to answer that question. And so these are the key talents you need in your organization, with roughly a proportion that I've shared here, to build this generic stack that we talked about and to build this infrastructure that we talked about. This is a little different from current industry. So usually when an industry decides, OK, we're shifting from rule-based to data-driven, they have to struggle with this as well. They have to reskill their employees. They have to upskill their employees. They have to change the proportions. And that's a hard change. That's a tough change. And most companies are going through that change right now. OK, so I've talked about all the positives and the future and the promise of machine learning. Let's get a little real. Let's talk about all the challenges that we have faced, and most likely you will also face. First, everything that I talked about, it's difficult to build. It takes specific and niche engineers, a lot of them. It needs data. Data is not cheap. It's not cheap to acquire data. It's not cheap to store data. We're talking about gigabytes and petabytes of data. This is large volumes of data. It's not easy to store data. So you need a lot of investment in your data infrastructure. And of course, once you start investing, of course, the organization or the business, which it should ask the question, what's your return of investment? What is your ROI? And that question is hard to answer initially, because your answer is like, I need to build first, I'll show you ROI later. That's not a good conversation, but that will be your challenge as you go towards this journey. 2, OK, you hire all these machine learning engineers, data scientists, software engineers, domain experts, but what you actually need is someone to get in a car, drive around, and collect data. That's an operational exercise. That is cars, hardware, maintenance, service, some acquisition car hits a pole. All things can happen, and you have to maintain those operations as a company. That's not your core expertise, but you have to do that. Third, the active learning loop. It looks really nice, doesn't it? But if one step doesn't talk to the other step, it just breaks. So if you use different tools for different steps, or you design them uniquely or independently, or one team does this tool and one team does that tool, there's no harmony in the tools. If there's no harmony in the tool, there is no flow in your work. If there's no flow in your work, there is no speed. And if there's no speed, there's no success. Back to the ROI discussion. So you really have to top-down decide what your tooling ecosystem has to be. You have to control that tooling ecosystem. That is actually the secret. And third, you're going to face, for at least a couple of months, a comment like this. Great technology, but my existing system already is better than your system. This is a constant comment. It's always the case. When you try to change an approach, the legacy system actually beats the new system initially. And it's a really difficult conversation, because your legacy system is doing its job 80% of the time, 90% of the time, and your system can barely keep in lane. And so it's a really difficult discussion. If you're able to push through all of this, I promise you the results are magical. You will go to a height that your system, your legacy system, cannot reach. And if your true goal is safety at scale, this is a transformation that you have to push through. So let me start wrapping us up. Where are we on our journey? As I mentioned before, there's the classical rule-based system, and there are many new approaches coming in the future. This area is rapidly developing. There is changes in the end-to-end approaches. There are different ways. There are different model architectures. There are different ways to train your models. We are somewhere in between. We want to be somewhere in between, because we are developing a safety-critical system. We want to deploy this system in hundreds, thousands, millions of cars with ultimate trust. So we believe explainability is important. We believe testability is important. We must be able to understand what our models are doing. We must be able to visualize what our models are doing. And we must be able to debug when something goes wrong. And that approach has led us to choose a hybrid stack where we have, of course, a very intense usage of machine learning, but an equally strict guardrail that allows us to drive on the road publicly and safely. Some of this you may have again seen in Area 2. Now, where the future takes us, we don't know, or we know, but we want to make sure that we go step by step and always keep trust and safety in forefront and make sure that our values are in line with Toyota. And lastly, why is our approach different? This is a technology that you can see in any other company. I would like to highlight a few things why we think we are a little different. One, as I just mentioned, we're not just chasing a trend. We're not chasing what's the latest paper that's published in machine learning. We don't want to be the latest and the best. We want to be comfortable, peace of mind, safe. And so for that, we highly believe in safety principles that Toyota has sharpened over decades of experience. They have experience in safety. They have experience in quality. We lean into that. We want to use those principles in the way we develop our software. We want to have safety-governed physical AI. We strongly believe in that. Second, it's a core principle of ours to be human-centric. What does that mean? Let me give you a couple of examples. One, that automated loop I showed you guys before, that needs engineers to make it work. Even if it's fully automated, someone has to supervise if each step is actually working. And that, I think, is a human touch. That's where the developers jump in. That's where the engineers jump in. That's where the testers jump in. That's where the drivers jump in. Two, we want our future Toyota and Lexus vehicles to drive in a way that gives you the ultimate peace of mind. It's not sufficient to be just safe and technically correct. Of course, those are table stakes. Of course, we have to do that. But we want you to get in the car and forget that an automated driving system is driving that car because it's so comfortable. It's so smooth. It anticipates everything. You don't feel anything in your belly, no G-forces. That kind of smooth driving only happens with experience. All of you, when you first got your driver's license, I guarantee you, were not smooth drivers. But over years, you've gotten smooth. But you're still not as smooth as some of the top elite drivers in Toyota. We refer to them as Sugo Udes, and we learn from them. These master drivers are masters at their art. And we let them drive our cars, and we collect data. We see how they drive the cars. And our goal is to make our stack drive like them. That's our ultimate goal as well. That's human touch. We lean into that. And lastly, I don't have to highlight this. The reason I'm here, the reason my team is so passionate and excited, is because safety at scale happens when you do changes at scale. And with Toyota, we have the ability not only to collect diverse data from around the world, from different kinds of drivers, from different regions, but also, once we learn from that and train from that, deploy this technology back to them at scale. Because ultimately, our goal, as I mentioned before, is zero accidents, zero mobility for all, and a continued autonomy experience for all of you. And with that, I would like to conclude my talk. Thank you so much for your attention, and I'm so happy to see you all here. Thank you so much.